this is your first time here, my name is Ali-Ayman and I'm an electrical and electronics engineering student. On this channel, I aim to make videos aimed at teaching STEM, so mainly mathematics, physics and chemistry. Other subjects I'll be teaching include economics, computer science, finance, and I will make videos on study techniques and productivity. This will be our fifth video on this series of videos named Atomic Structure. Make sure you watch the previous videos on this series if you haven't done so already to have some decent background knowledge before diving into later topics. Today we'll be looking at the electron arrangement in atoms in more detail, and we will start by explaining all the main concepts and then answering some practice questions at the end. So let's make a start then. So today the learning objectives are as follows. Know what an atomic orbital is and how many electrons it can hold. Know what sub-energy levels are, their different types, and how many atomic orbitals each sub-energy level can hold. Recognize which sub-energy levels exist in each main energy level. Be able to use SPD to write the electron configuration of an atom or an ion. And know the copper and chromium exceptions. These are just the chemical symbols for copper and chromium respectively. Just remember the highlighted sections are just there to help you understand the concepts more easily, but please pay attention to the whole thing so that what I'm saying actually does stick, because the remaining unhighlighted text is equally important for you to understand the crux of the more advanced topics we'll talk about later in this video and later in this series. So in order to discuss the more advanced topics we'll look at in this video, let's go over some basics we covered in a previous video on this same series. So let's talk about the basics of electron arrangement. Negatively charged electrons orbit the positively charged nucleus in main energy levels, so you can see them here. So this is the first main energy level, the second, and then the third. The maximum number of electrons that a main energy level can hold is determined by the formula 2n squared, where n is the main energy level number. So what this means is the first main energy level can hold up to a maximum of 2 electrons, because for the first main energy level, the main energy level number is 1, because it's the first main energy level. So we substitute 1 into n in this formula here, so we do 2 times 1 squared, which is the same as 2 times 1, and the answer to that is 2. The second main energy level can hold up to a maximum of 8 electrons. This time we use n equals 2 because we're looking at the second main energy level, so 2 times 2 squared is equal to 2 times 4, and that's equal to 8 electrons. Similarly, the third main energy level can hold up to a maximum of 18 electrons. This time we make n equal to 3, and 2 times 3 squared equal to 2 times 9, that's 18. And so on. This applies to the fourth main energy level and also the fifth. It's important to bear in mind that these main energy levels can hold up to a maximum. So they can hold less than 2, so the first main energy level can hold 1 electron. The second main energy level can hold, let's say, 4, 5, 6, or 3. Again, the key is up to. Don't think that it needs to hold 8. This is just the maximum capacity of the main energy level in question. And you can see it here. The first one can hold up to 2, up to 8, and up to 18. Another thing to bear in mind is that the further away from the nucleus the main energy levels are, the greater their energy. So we have increasing energy going from the first to the second to the third main energy levels. There's increasing energy. The last point is that the atom is kept together by the strong electrostatic forces of attraction between the positively charged nucleus and the surrounding electrons. And this is because unlike charges attract. So the electrons around the nucleus are negatively charged, and then, as we said in a previous video, the nucleus consists of positively charged protons and uncharged neutrons. So this means the overall charge of a nucleus is positive, and because that's the case, we have electrostatic forces of attraction between the surrounding electrons and the nucleus at the center of the atom. So there are sub-energy levels that exist within the main energy level. So in the previous slide, you'll recall we looked at the main energy levels. Now within these main energy levels, there's what we call sub-levels. And these sub-levels can each hold up to a certain number of the electrons present in the main energy level. And there are 4 types of sub-energy levels with increasing energy in this particular order. And they're called S, P, D, and F. So S has the lowest energy, F has the highest energy, because the F sub-level is further away from the nucleus than the S sub-level. And these sub-levels can hold different numbers of electrons. So the S sub-level can hold up to 2 electrons, the P sub-level can hold up to 6 electrons, the D sub-level can hold up to 10 electrons, and the F sub-level can hold up to 14 electrons. The number and types of sub-levels present within a main energy level depends on the main energy level number. So the first, second, and third main energy levels will all have different sub-levels, and we'll talk about which sub-levels are in which main energy levels in just a moment. So the first main energy level is only made up of an S sub-level. The second main energy level is made up of an S and a P sub-level. The third main energy level is made up of an S, P, and D sub-level. And the fourth main energy level level is made up of an S, P, D, and F sublevel. So the fourth main energy level has all the sublevels present. So the fourth main energy level is made up of all the sublevels we're talking about here. And the sublevel structures beyond the fourth main energy level will be covered in later videos. So here you can see we're talking about the first main energy level, here about the second, third, and fourth. And you can see here that the first main energy level just has the S sublevel, and S sublevels can hold up to a maximum of 2 electrons only. Here we have the second main energy level, and the second main energy level, as we said here, has both an S and a P sublevel. And because of that, as we mentioned before, the second main energy level can hold up to 8. Why is that? Well, that's because the S sublevel can hold up to 2, and the P sublevel can hold up to 6 electrons. So 6 plus 2 is 8. And then for the third main energy level, we have an S, P, and D sublevel. The S can hold up to 2 electrons, the P can hold up to 6, and then the D can hold up to 10. So 2 plus 6 plus 10 is equal to 18 electrons. And you'll notice that these numbers perfectly coincide with the formula we looked at earlier, 2n squared. It's just now we're looking at how many electrons each of these sublevels hold from the total number of electrons in the main energy level. And lastly, here we have the fourth main energy level. It has all 4 sublevels. It has the S, P, D, and F. So if we were to do 2 plus 6 plus 10 plus 14, the answer would be 32 electrons in total in the main energy level. Okay, so now it's important to clarify something before moving on, and that's the wave properties of electrons. So in 1926, this scientist called Erwin Schrödinger developed an equation that used the idea that electrons had some of the properties of waves as well as those of particles. And this is a very key point we'll look at, because in some models of the atom, we consider electrons as particles, but we can also consider them as waves, and that helps explain things like electronegativity and electron density. So this led to a theory called quantum mechanics, which can be used to predict the behavior of subatomic particles, and we'll look at this in more detail in later videos. Hopefully I'll make many series on quantum mechanics in the future, and if you're interested, this is how the Schrödinger equation actually looks like. So now let's look at the atomic orbitals. So an atomic orbital is a volume of space filled by a cloud of electrons in which there is a 95% chance of finding an electron. Orbitals can also influence the shapes of molecules. An atomic orbital can hold up to a maximum of 2 electrons. Both electrons in an orbital have a property called opposite spins. For now, you can think of it as the electrons spinning in opposite directions in their respective orbitals. Atomic orbitals are found in sublevels, and the number of orbitals present in a sublevel depends on the type of sublevel, whether it's S, P, D, or F. You also need to be aware of the number of orbitals present in each particular sublevel. So there's 1 orbital in an S sublevel, there are 3 orbitals in a P sublevel, there are 5 orbitals in a D sublevel, and 7 orbitals in a F sublevel. Since each orbital can hold up to 2 electrons, the number of orbitals in a sublevel indicates the number of electrons present in the sublevel. So if we look at the P sublevel, for example, there's 3 orbitals, and we said that each orbital can hold up to a maximum of 2 electrons. So to find the total number of electrons in a P orbital, we multiply the number of orbitals, i.e. 3, by the maximum number they can each hold, which is 2, so 3 times 2 is 6. And that perfectly coincides with what we were saying earlier, which was that P sublevels can hold up to 6 electrons, S sublevels up to 2, and so on. So here we have a table to make things look a bit more clear. So again, just like before, we have the main energy levels at the top here. So first, second, third, fourth. The first main energy level just has an S sublevel, and an S sublevel contains just 1 orbital, so it can hold just 2 electrons. The second main energy level has both an S and a P sublevel. An S sublevel has 1 orbital and a P sublevel has 3. We multiply the number of orbitals by the maximum capacity in each orbital. So 1 times 2, i.e. 2 electrons, and then 3 times 2, which is 6. And as we did before, 2 plus 6 is 8, and that gives us the total number of electrons in the main energy level. For the third main energy level, we have the different sublevels here. So S, P, D, and the number of orbitals in each sublevel is the same we discussed up here and before as well. So the S sublevel has 1 orbital, the P sublevel has 3, and the D sublevel has 5. We multiply each of these by 2 to find the number of electrons in each particular sublevel. So 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10. Then adding all these together gives us the total number of electrons in the main energy level, which is 18. And then similarly for the fourth main energy level, this time we have all 4 sublevels, so S, P, D, and F. We multiply the number of orbitals in the particular sublevel by the maximum capacity, which is 2. So again, 1 times 2, 3 times 2, 5 times 2, 7 times 2, we get 2, 6, 10, and 14. Then adding all this gives us the total number of electrons in the main energy level, as we discussed before. level. So atomic orbitals actually have different shapes. The s orbital has a spherical shape, as you can see in this diagram here. The p orbitals have a dumbbell shape with different orientations on the x, y, and z axes. We'll talk about the x, y, and z axes in this particular context in later videos. The d orbitals also have various shapes, so you can see them here. And the f orbitals have much more complex shapes, and we'll look at these in future videos because they can get a bit confusing. So now let's look at the electron arrangement in atomic orbitals. So atomic orbitals of lower energy are filled first. This is the key thing. So the lower main energy level is filled first, and within this level, sub-levels of lower energy are filled first. So this is what we discussed earlier. The first main energy level is filled before the second and before the third, but also within the main energy levels, the S sub-level is filled before the P sub-level, which is filled before the D sub-level, and so on. Atomic orbitals of the same energy fill singly before pairing starts. This is because electrons repel each other due to electrostatic repulsion, because like charges repel, obviously. No atomic orbital can hold more than 2 electrons. So in this diagram, we have squares here, and these squares represent atomic orbitals, and then this 1s, 2s, 3s, 2p. These represent the different sub-levels and the orbitals within each particular sub-level. So these 3 orbitals are denoted by p sub-level. You'll notice that there's a number 3 here, and that number 3 just basically means the p orbital in the third main energy level. Similarly, this s orbital here just means this s orbital is in the second main energy level. And then this 2p here just means that these 3 p orbitals are in the second main energy level. You'll notice here though, as we add more electrons to the 2p orbital, we add the first one here, one there. You'll notice as we add more and more electrons to the 2p orbital, as we said, atomic orbitals of the same energy will fill singly. So you can see here, as we add one more electron, we go from carbon to nitrogen, and each of the 2p orbitals is singly filled. You don't find this electron in the first 2p orbital. No, it's in the last one, and that's because of the electrostatic repulsion. You also notice that the arrows here, we have 2 different arrows. We have one pointing up and another pointing down, and they point in opposite directions in order to represent their opposite spins, and that's a property we discussed earlier. It's also important to note, not on this particular diagram, but the 4s sublevel is actually lower in energy compared to a 3d sublevel, and this is due to the overlap of sublevels the further away from the nucleus they are. And because of this, actually the 4s sublevel is filled before the 3d sublevel, with the exception of 2 elements we'll discuss shortly. So let's look at different ways to represent electron structures. There is a shorthand way of representing electron structures, and here's an example for the sulfur atom in particular, which has 16 electrons. So you can see here we have a 1s2, 2s2, 2p6, 3s2, and 3p4. That's the way you read it, by the way. The letters S and P represent the different types of sublevels, the ones discussed earlier. The numbers 1, 2, and 3 represent the main energy level numbers, and therefore help identify which main energy level is housing any particular sublevel. So is the P sublevel in the second main energy level, or is it in the third main energy level? Similarly, is the S sublevel in the third, second, or first main energy level? So again, these numbers help us identify which main energy level houses any particular sublevel. The above representation, so this thing here, can be rewritten in order to take orbitals into account, and we can write it like this instead. This time the 3 different orbitals in the 2p and 3p sublevels are denoted by the x, y, and z subscripts. No subscripts for the s sublevels are needed because s sublevels have only one orbital, so we don't need to write any x because there's just one orbital in the s sublevel. Noble gases can also be used to further simplify this shorthand notation, as can be seen in the case of a calcium atom, which has 20 electrons, by the way. The argon atom is used, this is the calcium atom, and instead of denoting it like this, we can instead simplify this. We can get rid of the initial 1s2, 2s2, 2p, whatever there is. We can get rid of that beginning and instead just replace it with a noble gas chemical symbol in square brackets. And the reason for that is, in this particular case, the argon atom is used because it has 18 electrons and calcium has 20 electrons. So argon can therefore be used to help represent the electron structure because 18 is less than 20. So 18 can make up for many of the electrons in the calcium atom without going over the 20 mark. We have the 4s2 here to represent the remaining 2 electrons that are not accounted by the argon. So again, these are more examples here. So here's an example for krypton with this particular representation, just showing the sublevels. So krypton has 36, so we write it as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. With the calcium atom, again, this time not using the argon symbol, we would write it as 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So you can see what we did did before, we just replaced all of this with the argon. That's why this is like much more shorthand way of writing the electron structure of calcium. Here we have examples for boron, carbon, and nitrogen using the X, Y, and Z subscripts. So copper and chromium atoms are an exception to the following rule I mentioned before, and that rule was atomic orbitals of lower energy are filled first. The atoms of these two particular elements break this rule, and this exception exists because in copper and chromium atoms the 4s orbital is always half full, and the 3d orbitals contain electrons despite the fact that the 4s orbital is half full. We said before that the 4s and the 3d sublevels overlap, and the result was that the 3d sublevel becomes higher in energy than the 4s sublevel. So if this above rule were fulfilled, the 4s sublevel would fill first before the 3d sublevel or the 3d orbitals are filled. But that is not the case when it comes to copper and chromium atoms. So again, just to reiterate what I said, although a 3d sublevel is higher in energy compared to the 4s sublevel, the 3d orbital still contains electrons despite the half-full 4s orbital. So here are the electron configurations of copper and chromium atoms. This is not using the X, Y, and Z, this is just showing the sublevels. So here we have 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. This is half full, but we have 3d10. So electrons have already filled the 3d sublevel despite the fact that the 4s is still half full. And again, copper has 29 electrons. Similarly for chromium, we have the electron structure is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. It's also half full just like before, and then 3d5. And chromium has 24 electrons. So now let's answer some summary questions. Okay then, so here are the summary questions. Feel free to attempt these now before watching me do so. So pause the video, attempt these questions. Once you're done, you can resume and then compare your answers to mine. So the first question says, give the full electron arrangement for phosphorus. In order to do this, we need to know how many electrons one phosphorus atom contains. So I'll just import the chemical symbol and show you how it looks like. So this is the chemical symbol of phosphorus, and then this is obviously the atomic number and the mass number. We're interested in the atomic number because that gives us the number of electrons. So a phosphorus atom contains 15 electrons. So the question wants us to give the full electron arrangement for phosphorus, given the fact that it has 15 electrons. So we start by filling the first sublevel, which is the 1s. We put 2 electrons in the 1s sublevel. Next comes the 2s sublevel, and we put 2 electrons in that. Next comes the 2p6 sublevel, and 6 electrons go in the 2p sublevel. Since we have enough, there's 15 electrons. And next we have 3s sublevel. We can afford to put 2. And then comes the 3p sublevel. So we've used up 2 plus 2 plus 6 plus 2. That's equal to 12. That leaves us with 3 electrons left because 15 minus 12 is 3. So this 3p sublevel can hold maximum of 3 electrons for phosphorus, obviously. So this is the full electron arrangement for phosphorus. Part B says give the electron arrangement for phosphorus using an inert gas symbol as a shorthand. So it's talking about the noble gas notation we looked at before in square brackets. So let's look at the periodic table to see which noble gas has an appropriate number of electrons to help us write this electron arrangement in a more shorthand way. So here's a picture of the periodic table. Phosphorus has 15 electrons, so let's zoom in and see which noble gas has just less than 15 electrons, and therefore enough to simplify this shorthand notation we have here. So we can't use argon because argon has 18 electrons. We can use neon because neon has 10 electrons, that's less than 15, and therefore the only particular noble gas appropriate. We can use helium, but we would need too many of those. Using neon would simplify the notation a lot further. So to rewrite the notation, we write neon like this in square brackets. So neon has 10 electrons and 15 minus 10 is 5, so there's 5 more electrons left. So phosphorus has 15 electrons, neon has 10 electrons, 15 minus 10 is 5. There's 5 more electrons we need to denote, and the 5 outermost electrons are the ones in the 3s and 3p sublevels. So we just write this down here. And that's how we write phosphorus using an inert gas symbol as a shorthand. So question 2 says, give the full electron arrangements of the calcium ion and the fluoride ion. So calcium has 20 electrons. So the calcium atom has 20 electrons. The ion is Ca2+, so the calcium atom will need to lose 2 electrons in order to become an ion. That would leave us with 18 electrons. So the calcium ion has 18 electrons. So now let's write the electron configuration. So there's 18 electrons in a calcium ion. So we write the electron arrangement like this. So it's 1s2, 2s2, 2p6, 3s2, and then 3p6. So That's the electron arrangement of calcium ion. Now for 2A the question asks us to find the electron arrangement of a fluoride ion. A fluorine atom has 9 electrons, so a fluoride ion has 10 electrons, because a fluoride ion has a charge of -1, so it therefore has to gain 1 electrons to become an ion. So we'll write the electron arrangement of a fluoride ion with the 10 electrons. So it will look like this: 1s2, 2s2, and then 2p6. 2 plus 2 plus 6 is 10, so that's the electron arrangement for a fluoride ion. Now for part BI, the question says give the electron arrangement using an inert gas symbol as a shorthand. Well, looking at the periodic table from earlier, the argon atom would be suitable because it has 18 electrons, and the calcium ion also has 18 electrons. So to rewrite the calcium ion electron arrangement, we can just use the argon symbol like that. For the fluoride ion, there's 10 electrons. The neon atom has 10 electrons, so the neon atom shorthand would do just fine. So we will just write neon here. And those are the final answers for question 2. Now let's look at some practice questions from past papers. Right then, so let's answer this question here. So first of all, let's read what this question 17 here says. The question is about atomic structure. In the 19th century, J.J. Thomson discovered the electron. He suggested that negative electrons were found throughout an atom like plums in a pudding of positive charge. The diagram shows an atom of element R using the plum pudding model. An atom of R contains 7 electrons. The question says, state 2 differences between the plum pudding model and the model of atomic structure used today. So we talked about the plum pudding model and other models of the atom created before the current one. So this particular scientist was in the 1800s. There were other scientists as well who made other models of the atom or made certain assumptions. But basically, just like the question says, Thomson thought that electrons were dotted in a sphere of positive charge like plums in a pudding. This is not the model of the atom used today, and the question wants us to cite 2 differences between this plum pudding model and the model of the atom used today. So one difference would be that in today's model of the atom, we have positively charged protons and uncharged neutrons in the nucleus of the atom. Alright, so this is the answer to part A. Now the question wants us to deduce the full electron configuration of an atom of element R. The first thing we need to do is we need to find the number of electrons in element R, and we count them using this diagram here. So we have 1, 2, 3, 4, 5, 6, 7 electrons. The reason why we've done that is because in an atom, the number of protons must be equal to the number of electrons because atoms have an overall charge of 0. So the element with 7 electrons would be nitrogen. So we have to write the electron configuration for element R, and that would look like this with 7 electrons: 1s2, 2s2, and then 2p3. Part C says identify R and deduce the formula of the compound formed when R reacts with the group 2 metal in the same period as R. Well, R is nitrogen, and the group 2 metal in the same period as R is beryllium. So this will be an ionic compound. We'll talk about how to write ionic compounds soon. What we basically do is we write the respective ions. So the beryllium ion has a 2+ charge because it's in group 2, so it will lose 2 electrons. The nitrogen ion has a 3- charge because it needs 3 electrons to obtain a stable outer shell. It needs to gain 3 electrons to obtain a stable outer shell. And what we do now is we bring down the charges like this. This is like a trick you can do. And once you've done that, you end up with this: beryllium 3 and 2. So this is the compound which forms when R reacts with the group 2 metal in the same period as R. So now let's look at this question 18A. We'll just do part A because the other parts to this question will then refer to a topic which we will cover in the next video. So it says write the full electron configuration for each of the following species: chloride and iron 2+. A chlorine atom has 17 electrons and needs 1 electron to obtain a stable outer main energy level of electrons identical to that of a noble gas, as we discussed in previous videos. We need to write 18 electrons: 1s2, 2s2, 2p6, and 3p6. Now if you were to add these, 2 plus 2 plus 6 gives us 10, and then plus 2 plus 6 gives us 18, and that's the number of electrons you find in a chloride ion. As you can see here, iron has 26 electrons, and the particular ion we're looking at will have 24 electrons because it's an iron 2+, so this iron atom will need to have lost 2 electrons. So to represent 24 electrons, we write it like this: 1s2, 2s2, 2p6, 3s2. The reason we wrote 3d6 was because the 4s2 is actually lost before the 3d6, despite the fact that the 3d sublevel is higher in energy compared to the 4s. The 2 electrons in the 4s sublevel are still lost before those in the 3d sublevel. So here's a multiple choice question. The question says, what is the electron configuration of vanadium 2+ in the ground state? The first thing we need to do is we need to determine the number of electrons in a vanadium atom. And the answer to that is 23. So I think the best thing to do is to write the electron configuration first without the 2 electrons lost. So it would look like this: 1s2 for 23 electrons, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d3. When it says here in the ground state, what this basically means is that the electrons in the vanadium 2+ ion are not at any point experiencing electron excitation. That basically means electrons in one main energy level or sublevel gains energy and is excited or gains enough energy to jump to the next energy level. That's what this basically means. It's just saying that that's not happening in this case. So it says vanadium 2+, so this means 2 electrons were lost by the vanadium atom. We said before that the 4s electrons are lost before the 3d electrons, so we can just cross out those 4s2 because 2 electrons are lost, and we're left with 1s2, 2s2, 2p6, 3s2, 3p6, and 3d3. So the answer to this question is A. Alright then, so this brings us to the end of the video. I hope this was of great value. I hope you benefited from this video. If you have any questions, please post them in the comments. I'd be more than happy to help out, help you progress more generally speaking. If you find these videos useful, don't forget to subscribe, and more videos are coming soon, so please watch out for those videos. Thank you for watching and see you all next time. Goodbye.